Okay, so here in this video, we're going to start applying derivative rules to answer other questions. So basically, in the prior chapter, we learned how to take derivatives, and now we're going to learn how to apply them. So the first thing is, we're going to apply it to graphing a function. So f of x equals, well first, before we do that, let's do a little quick recap. If this is a sketch of f, if I draw tangents along the curve, as such, I would notice that when the slope of the tangent is positive, it's positive here, 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 0, negative, 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 0, positive, 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 etc. That when the slope of the tangents are positive, that is, f prime is greater than 0, we would notice that the function f is increasing when the slope of the tangents are positive. So when f prime is greater than 0, this would imply that f is increasing on those intervals. When the slope of the tangents are negative, that is, f prime is less than 0, that would imply that f is decreasing, meaning it's falling. We could see up here, this is where f prime equals 0, here and here. So we call this point where f prime changes signs from positive to negative a relative maximum. A relative maximum occurs when f prime changes signs from positive to negative. Here, at this point where f prime changes from negative to positive, is called a relative minimum. F prime changes signs from negative to positive. And the points where f prime equals 0, or perhaps a D and E, as long enough the point, which we often call C, is in the domain of the function, we call this number a critical number. Okay, and we'll get more into that in the next section. But a critical number, by definition, is where f prime equals 0 or a D and E. Like in the absolute value graph, right here at the corner point. The derivative does not exist, but yet at this corner point, it would be a local minimum, as well as because it's the lowest point on the graph, it would be called an absolute min. Remember, we're calling these relative maxes, or local maxes, or relative mins, or local mins, because these are just the highest points and the lowest points around the other points. So this may not be, if this graph continues all the way, if it started from a negative infinity direction, this would not be the lowest point on the graph. But in comparison to the points around it, it is the lowest point. So we call it a local minimum. Up here, because in comparison to the points around it in a neighborhood, that this is the highest point, we would call it a local maximum or a relative maximum. Okay, and again, because this graph would maybe continue going off for x greater than, x off to infinity, the y's are also getting bigger and bigger, we would have no absolute maximum either, unless perhaps we started to close things off. But that's getting away from the idea. Okay, so relative max is when f prime changes signs from positive to negative. Relative min occurs when f prime changes signs from negative to positive. Our critical numbers are found by taking the first derivative, setting it equal to 0, or where it's a D and E, and just make sure that that number is in the domain of the function, meaning we don't get a 0 in the denominator, or perhaps the square root of a negative. Now, we would also notice that, say, from here to here, okay, the slopes are positive, and they're getting less positive, then 0, negative, negative, and maybe right about here, they start to get less negative. So from here to here, we would say that the slopes of the tangents, which are f primes, those are our slopes, are decreasing. Well, any function is decreasing, as we saw up here, then its derivative would be less than 0. So then if f prime is decreasing, then its derivative, which would be f double prime, would be less than 0. From here on out, we would notice that they get less negative, 0, positive, and more positive. So here, f prime is increasing. Well, any said function increasing would mean that its derivative, which in this case would be f double prime, would have to be greater than 0. So notice that when f double prime is less than 0, the graph of f is concave down from here to here. From here to here, when f double prime is greater than 0, the graph of f is concave up. This point, where it changes from concave down to concave up, is called a point of inflection. The point of inflection occurs when f double prime changes signs. Okay? All right, so now let's put it together to solve a simple problem and to graph it. So suppose we have f of x equals x cubed minus 3x squared plus 1. So f prime of x equals 3x squared minus 6x. We're going to set it equal to 0, and we're going to factor out a 3x, and what's left is x minus 2. Set each of these pieces with an x equal to 0, and these right here are technically called our critical numbers, c. And obviously I can take both these numbers, put them back into the function, and get back a real number. So they are in the domain of the function. Next, I'm going to make a number line using those critical numbers to find out when f prime is positive and negative. If I pick something to the left of 0, like negative 10, and put it into f prime, I get a negative times a negative is a positive. If I pick 1, positive times a negative is a negative. And if I pick, say, positive 10, I get a positive times a positive is a positive. So when f prime is positive, f is increasing. When f prime is negative, f is decreasing. When f prime is positive, again, f is increasing. We do not accept number lines as answers, so we have to write it using interval notation. So f is increasing, and we should say f. F is increasing on the interval from negative infinity to 0 in union with 2 to infinity because f prime is greater than 0 on those intervals. F is decreasing on the interval from 0 to 2 because f prime is less than 0 on those intervals. We have a relative max at x equals 0 because at 0, f prime changes signs from positive to negative. So there's a relative max at x equals 0 because f prime changes signs from positive to negative. We have a relative min at x equals 2 because f prime changes signs from negative to positive at x equals 2. And now we'll proceed to the second derivative, f double prime. Sometimes it pays off to go before you simplify. So that would be then 6x minus 6. Set it equal to 0. And x would be equal to 1. So now I'm going to run a number line test on 1. This gets labeled f double prime because the sign of this tells us what f is doing. So if I pick, say, 0, put it into f double prime, I get a negative. If I pick, say, 2, I get a positive. So this tells me f is concave down and f is concave up on that interval. So concave up from 1 to infinity because f double prime is greater than 0. Concave down from negative infinity to 1 because f double prime is less than 0. This is where f double prime changes signs. So at x equals 1 is a point of inflection because f double prime changes signs from negative to positive there. Okay, we do have to justify our points of inflection. It also occurs where f prime changes from decreasing to increasing. Okay? Alright, so now we've got all the key ingredients to make a graph of this function. Again, in this chapter, we're learning how to use derivatives to make a sketch of a function. So again, I start out by taking the first derivative, set it equal to 0, get the critical numbers, make a number line test on f prime, where f prime is positive, f is increasing, where f prime is negative, f is decreasing. Justify the relative extrema, max because f prime changes signs from positive to negative, and a min because f prime changes from negative to positive. We don't want because it changes. We don't know what it is. Or we don't say because the function. What function? You have to be very clear as of what function is changing signs. We then take the second derivative, set it equal to 0, do a number line test on that number. Where f double prime is negative, f is concave down. Where f double prime is positive, f is concave up. And if it changes signs here, then that constitutes a point of inflection. And now we need to make a sketch. So what I need is to, first of all, erase some of this. And I need to make a chart with the key information. And what goes into that chart are my extrema values, 0 and 2, and my point of inflection at 1. Put 0 into the function and I get 1. 2 cubed is 8. 2 squared is 4, times negative 3 is minus 12 plus 1. Negative 4 plus 1 is negative 3. Put in a 1. Negative 2 plus 1 is negative 1. Okay, so now I have that information. What I next need is the slope of the tangent at every point of inflection. And at this one, it's 1. So to go for the slope, we should all know we go to f prime, which was erased. So I'll put it back. I'll put 1 into my derivative, and I'll get from my slope 3 minus 6, which is negative 3. Okay. And then now I do need to keep the second derivative graph. That's going to be important to me. So here's how I make my sketch. First of all, what could get to be a challenge are these numbers. If these numbers are very big, you have to decide what you want to count by on the y-axis as well as the x-axis. The y-axis is more of the concern. So these numbers are pretty small, so I'll count by ones. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the first thing you're going to graph is every point of inflection. So my point of inflection is 1, negative 1. And what I do is I put an x there because it's a very important point. At that point of inflection, I'm going to graph the slope of the tangent line, which is negative 3. Because I'm counting by ones from this point, I'll go down 1, 2, 3, and to the right one. Then I'll go up 1, 2, 3. 1, 2, 3, and the left one. And just faintly put in that line. The greater the slope is, it will kind of seem uneven and not connect so nicely to form a line, but you're only using it as a guide. So again, what did I do? I graphed a point of inflection. If I have more than one, I graph both. And at each point of inflection, I'm graphing the slope of the tangent line. And that came from putting 1 back into f prime. Now I'll graph my points 0, 1, and 1, negative 1. Not 1, negative 1, 2, negative 3. Okay. If you recall, at 0 was a relative max, and at 2 was a relative min. Starting at the point of inflection, which is right here, from the second derivative test, right over, well, the second derivative number line, that is, from f double prime to the left of 1, the graph is concave down. So you put your pencil on the point of inflection, you start out hugging the tangent line, and be concave down. But before, as you're concave down, you have to reach to what is the relative maximum. Now, using your F double prime number line to the right of 1 at that point of inflection, you are concave up. But you can't skip out on the local minimum. So you start at the point of inflection, and you start out hugging it, means you're pretty close, reach the minimum, and be concave up. So when you smooth it out, like this, there's something very important to look for. 1, we better be turning around up here at 0, 1. And we better be turning around down here at 2, -3. Relative max, relative min. It's where F prime changes signs from positive to negative, and then from negative to positive. This is where F double prime had equal 0 and it changed signs. What's very important is that if we did something like this and reached to that minimum, what happens is right here at this tangent line, when I'm concave up, the tangent line has to lie below the curve. When you're concave down, the tangent line has to lie above the curve. So that would make this sketch inaccurate. Back at the beginning, when I had originally sketched it like this, notice that when I'm concave up, the tangent line is below the curve, which would mean then any tangent line approximation near this would be less than the actual value, because the graph is concave up, so the tangent line lies below. Here, when I'm concave down, the tangent line lies above the curve, so any approximation being used off the tangent line would be greater than the actual value, because the graph of F is concave down from here to here, and the tangent line lies above. So it's very important to realize that when the graph is concave up, the tangent line lies below the curve. When it's concave down, the tangent line lies above the curve. And that is how we used the first derivative along with the second derivative to make a sketch of this function. We could never get these turning points without the use of calculus. It will tell us exactly where the function changes from increasing to decreasing, and vice versa.